Hello and welcome to topic 7.1. Here we go. We start with a right triangle. Now most of you know or can recall from the past that if you start with a right triangle with A, B, and C, that you get this equation, a squared plus b squared equals c squared. But question is why? Why do you get this equation if you have a right triangle? So, and it turns out that it's magic. It's just magic. It just works. It just does. Nobody knows where this equation came from or how it works. We just know that it works, and that's it. Someone told us a long time ago that if you have a right triangle, A, B, and C, that a squared, b squared equals c squared. All right, so that's just the way it is. There's magic in the world. Just kidding, we can prove it, and here's how we'll prove it. We're going to do this. We're going to take and draw what's called an altitude. And by drawing the altitude that then splits, I'm gonna call this x, this part, I'm gonna call this y, and I'm gonna call this z. All right, now watch what we can do. Go back to 6.4. We can now take these triangles apart. All right, we got A, B, and C. That's the big triangle. We have the medium triangle, and I'm going to reorient it. The medium triangle has short leg Z, long leg C. Oops, that was wrong. Long leg C, that's the hypotenuse. Come on, eraser. There we go. Long leg C, and then this would be the hypotenuse of this triangle right here, so B. And then the smallest of the three, right here, has short leg X, long leg Z, and hypotenuse A. All right, now I can find some proportions in here. For example, if I look at this portion, I have A is to C as X is to A. And then I can cross multiply, which gives me A squared equals CX. Let's do that again. I can do the same exact thing, this time with this proportion, and I get B is to C as C is to, oh, hold on, as C is to, this was supposed to be Y. No. Shoot. This was Y. This was the long leg of the medium. The long leg of the medium is Y. There you go. So let me do that again. C is to B, or B is to C as Y is to B. There we go. Y is to B. That's the way it's supposed to be. Even I got that mixed up. That's supposed to be Y right there. And then you cross multiply like that. And look at that, we got our A squared and our B squared. So what happens if we add A squared plus B squared? If I add A squared plus B squared, that would be the same as adding CX plus CY, which would be the same as, we can factor out an C from this. And what does X plus Y equal over at our picture? If I take X and add it to Y, I get back to C. So this is like C times C, which is C squared. So we have A squared plus B squared equals C squared. So we just proved it. It's no longer magic. And there you have it. Now you can use the Pythagorean theorem to do that. If you're online, you can go and watch this video, and it's a couple more proofs of the Pythagorean theorem. They're way more fun. It's all visual proofs. It's not analytical proofs. So go check that out. All right, next, write the answer in simplest radical form. All right, so here we have a right triangle, and all we need to do is just solve for x. So it's a right triangle. This is a leg. This is a leg. This is your hypotenuse. And we're going to use a squared plus b squared equals c squared. But really what that means, it's really leg squared plus leg squared equals hypotenuse squared. Okay, so here we're just going to do, let's just plug it in like that. And so this would be 6 squared plus 6 squared equals x squared. So that would be 36 plus 36 equals x squared. That would be 72. And now I'm going to flip it around because I like to have my x on this side. All right, now to get rid of a square, you square root. So that cancels off. A square and a square root cancel each other off. So we're left with x equals the square root of 72. All right, now if we were in middle school, because you did learn this in middle school, if we were in middle school, we would just plug in the square root of 72 and get that as our answer. So about 8.5. If we were in middle school, we'd say x is approximately 8.5. Call it good. But we're not in middle school, so we need to break this down into what's called the simplest radical form. All right, so the square root of 72. So, best way to do this is to take 72, and we're going to think about how many ways we can multiply 72. You can do 72 times 1, you could do 36 times 2, you could do 24 times 3, you could do 18 times 4, you could do 12 times 6, and you could do 9 times 8. All right, those are your options. All right. Now, what you want to do this the least painful way possible is you want to find the one of these that has perfect squares. So find perfect squares. Now, perfect squares are these numbers: 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, goes on, right? So find one that has one of these in it. So not this one. This one works. Not this one. Not this one's got one. And not this one. And this one has one. All right? So then you pick the one that has the largest one of these numbers, and that's the easiest way to do that, I think. So this would be our winner. 36 is the largest perfect square. So what I would then do is I would take this root 72 and I would break it down into 36 times 2, which then can be further broken down like that, which then can be further broken down into 6 root 2. So that's the answer we need to come up with in geometry class. 6 root 2. Now watch, if I do root 72, I get that number. And if I do 6 root 2, I get that number. All right? So there you go. What if I would have used 9 and 8? What if I would have broke it down using 9 and 8? Well, let's take a look. Root 72 can be broken down into 9 times 8, which can then be broken down into 9 times 8, which can then be broken down into 3 root 8. And that's good, but 8 can be broken down into 4 times 2, which can then be broken down into 4 times 2, which can then be broken down into that, which is 6 root, back to 6 root 2. So either way you go, you're going to get 6 root 2, but if you pick the option that is the largest perfect square, then you don't have to do the breakdown thing twice. All right, but that is going to be a skill you're going to have to do. You'll have to do that. So try this one. I'll get you started. This is a leg now. So when we're doing a squared plus b squared equals c squared, we have to plug x into the a or the b. It doesn't matter which one. And our hypotenuse is c. Remember, the legs always make the right angle. That's how you know what the legs are. X and 8 are making the right angle. Okay, so now just work this out. Okay, see what I did there? I subtracted, I squared, I subtracted over, I square rooted to get rid of the square, and now I'm here, I'm at 192. Now you gotta think about what you could take out of 192. So pause the video and try breaking down 192. Okay, 192 times 1, obviously. 192 divided by 2 is 96. 96 and 2. 192 divided by 3, you got 64 and 3. Now, just stop right there. You found it. There it is. It's 64. I just kept breaking it down until I got a perfect square. 64 and 3 is the one we're going to use. So I'm going to take 192 and I'm going to turn it into 64 times 3, which then 64 and 3, which then turns into 8 root 3. That is the answer we're looking for, 8 root 3. All right, let's do another one. Getting even more tricky, putting square roots into the A and the B part and the C part. All right, these are your legs. Look at your right angle. So these are your legs, this one and this one. So if I do a squared plus b squared equals c squared, I'm going to end up with x squared plus 2 root 5 squared equals root 47 squared, like that. Now, I highly recommend that when you're doing this, especially when you got roots like this, you put parentheses around this, because you have to square the whole thing. You're not just squaring root 5, you got to square 2 root 5. All right, now this one is tricky. Let's think about this, and you will have to do this on your test. All right, now let's skip this one for a second. Let's come back to it. Root 47 squared. This is easy. These just cancel out. Root 47 squared, I can show you in your calculator if you really need to. But if I do the square root of 47 and then square it like that, root 47 squared, it's just 47. They cancel out. Those things cancel out. So this is just 47 right here. What is 2 root 5 squared? Well, let's take out another sticky note. 2 root 5 squared. Let's break it down into what that actually means. 2 root 5 squared. What that means, when you square something, it means 2 root 5 times 2 root 5. All right, so let me show you what's happening here, that you're multiplying all of this. Now when you multiply, it doesn't matter the order you multiply, so we could call that 2 times 2 times root 5 times root 5. We could do that, which then, look at this, what's 2 times 2? That's 2 squared. And what's root 5 times root 5? That's root 5 squared. All right, so really this right here turns into this. So it's almost like you're distributing the square. You're squaring the 2 and you're squaring the root 5. All right, so it turns into that. You're squaring the 2, you're squaring the root 5. But it's not technically distributive, it's like applying. You're applying the square to both of those things. All right, so then this ends up just being 4, and this ends up just being 5, because those cancel out. And so the answer is 20. So if I were doing this problem, if I had 2 root 5 and I had to square it, what I would do, I would say, okay, what's 2 squared? What's root 5 squared? What's 4 times 5? 20. That's what I would do. But watch what your calculator does. Look at this. If I do 2 root 5 squared, if I plug it in just like that, will I get 20? No, it didn't give me 20. Why? Because your calculator is only squaring the root 5. We got to make it square the 2. So you need to put it in parentheses, 2 root 5, like that. You got to put 2 root 5 inside the parentheses, and then there's a square button. If you haven't known, this is your square root, and there's your square button. It's probably on your calculator somewhere, and they're probably the same. But there you have it, and then you square it, and you get 20. All right? Or you could do 2 root 5, press enter, and then square the answer, and that's essentially doing the same thing. So the answer is 20 for that. So we'll plug that in. There's 20. Now we will subtract, and we will square root. Now this one's easy to break down, 27. There's really only one way to break that down, and that is 9 times 3. Which is 3 root 3 is my final answer for that one. All right, yes, you will have to do questions like this where you have to break them down. Okay, next are things called Pythagorean triples. Now look at these. Look at these up here. All of these 6, 6, 6 root 2. This ended up 6 root 2. If it's got a root in it, then it's not a Pythagorean triple. This one ended up 8, 16, 8, and 8 root 3. So when an 8 turns up as a length, it's not a Pythagorean triple. This one obviously is not a Pythagorean triple, but there are certain ones that work when you plug them into the Pythagorean theorem, and those are called Pythagorean triples, and they don't have any roots. So when there's no roots involved, and it works in the Pythagorean theorem, for example, 3, 4, 5 is the most famous. 3 squared plus 4 squared equals 5 squared. Let's check it out. That would be 9 plus 16. What's 9 plus 16? 25. What's 5 squared? 25. It works out. It's checked. See? So that works. Not only does 3, 4, 5 work, but also any multiple of 3, 4, and 5. So like 3 times 2, 4 times 2, 5 times 2, or 3 times 3, 4 times 3, 5 times 3. So watch. 6, 8, 10 works. 6 squared plus 8 squared equals 10 squared. That's 36 plus 64. What's 36 plus 64? 100. What's 10 squared? 100. See, it works. All right. So any multiples of 3, 4, and 5 work. For example, look at this problem. This is a Pythagorean theorem question. Just like up here. We have to solve for the leg. I could use a squared plus b squared plus c squared. So do you understand that you could still use a squared plus b squared equals c squared? However, there's a shortcut to this one because I see that this is 3 times 11 and this is 5 times 11. Therefore, 3, 4, 5, 3, and 5. This one has to be the 4. So 4 times 11. So 44. It has to be 44. All right, we can easily check in our calculator to make sure we got it right just by doing 33 squared plus 44 squared and seeing if it is equal to 55 squared. Ah, I did it right. They're equal. That's what we're supposed to get. All right, next one. There's other Pythagorean triples, 5, 12, 13. And any multiple of 5, 12, 13. And it keeps going on forever, by the way. And then there's more. There's work, that's a Pythagorean triple. There's other ones, and this goes forever. These are just some examples. So it goes forever that way, and it goes forever that way. Let's look at this one again. We could use a squared plus b squared equals c squared. However, this is 15 times 5. This one is 15 times 3. That's a 3, and that's a 5. What are we missing? The 4. This one must be 15 times 4. So it's got to be 60. So I was able to solve for that without using the Pythagorean theorem. And it took me a fraction of the time that I could see. So if you look at something, to really keep these ones in mind. So look, all right, let's see here. Oh, let's see here. Does that divide by 5? Does this hypotenuse divide by 5? If it does, then you want to look and see, does the leg divide by 3 or 4? All right, so 80 divided by 5 is 16. This is 16 times 5. And this one divides by 4. That's 16 divided by, that's 16 times 4. So that makes this one, we got 3, we got 4, we got 5, we need 3. 16 times 3, so 48. Did I have to use the 3, 4, 5? I used the 3, 4, 5. Did I have to use that? No, but it saved me time because I could see it. All right, next one. This one's a little bit better. Does this hypotenuse divide by 5? It does. That's 8 times 5. Does this also have an 8 in it? Ooh, it does. That's 8 times 4. So what's this one have to be? 4, 5, what are we missing? 3. 8 times 3. 24. Did I have to use 3, 4, 5? No. Could have used Pythagorean theorem. Look at this one. Does that divide by 5? I'm thinking 3, 4, 5 maybe? No, it doesn't divide by 5. What does it divide by? That is 3 times 13. Ooh, 13. Look at this one, 5, 12, 13. Is there one of these that divides by 12 or by 5? Ooh, this is 3 times 5. Ooh, 5, blank, 13. 5 and 13, 5 and 13, ooh, we're missing 12. So this one must be 3 times 12. So 36. All right, do I have to know all of these? No, but I would know these two. These two are used quite a bit in making Pythagorean problems in SAT. I've never seen an SAT problem that was a right triangle that wasn't a 3, 4, 5 or a 5, 12, 13. Look at this one. Ooh, okay, that divides by 5. That's 5 times 5. Is this 4 times 5? Is it 3 times 5? Okay, so this is not a 3, 4, 5. I don't know what this is. So I'm just gonna have to do the old Pythagorean theorem. All right, so we got x squared plus 24 squared equals 25 squared. Now watch, I'm gonna plug this into my calculator very easily at this point. Just take the 25 squared and subtract the 24 squared. 49. So x squared equals 49. Oh, x equals 7. Oh, that was a Pythagorean triple, wasn't it? There's no roots, so x being 7. Oh, that was just right here. That was this one. I don't have that one memorized though, so I had to use the old-fashioned way. So if you don't have these memorized, or if you don't see the relationship, then you can always use a squared plus b squared equals c squared. It's just gonna take you a little bit longer. All right, last thing. We know that in a right triangle, a squared, so if this is a, and this is b, and this is c, we know that a squared plus b squared equals c squared. Let me rewrite that. Let me write that backwards. This is what we're gonna do. We know that c squared would equal a squared plus b squared. All right, what about if the triangle had an obtuse angle instead of a right angle? You see how this gets quite a bit bigger? This would have to be larger. If this is a larger angle, then that makes C a little bit of a longer piece. And in that case, it turns out that C squared would have to be greater than A squared plus B squared. All right, so you can tell if 3 lengths make an obtuse angle if the largest part is greater. And then likewise, if you have an acute angle, you can see that would have to be smaller. So C squared would be smaller than A squared plus B squared. All right, and that's basically the last theorem. If C squared is equal to A squared, we have this scenario right here. We have a right angle. If c squared is less than, if it's smaller, if this ends up being smaller, it makes this an acute angle. So that's acute. And if c squared is greater, it's obtuse. But really the first thing you want to do is figure out largest side. And that's going to be your c. Figure out your largest side. That will be your c. All right. So, with that said, do the lengths 7, 14, and 16 make a right triangle, an acute triangle, or an obtuse triangle? So here's the process you do. You pick the largest side, so in this case 16, and you look at 16 squared and compare it with 7 squared and 14 squared. How do they compare? How do those two things compare? We're comparing c squared with a squared plus b squared. So 16 squared is 256, and 7 squared plus 14 squared, you can do that all in your calculator, 245. So how does 256 compare to 245? 256 is bigger, which then would imply obtuse. So this makes an obtuse triangle. All right, try this one. Pause the video and try it. Do what I just did. All right, pause the video, and you're back. Pick out the largest and compare it against the other two in a Pythagorean theorem way. So 61 squared, I got 3721, and 11 squared, plus 60 squared, 11 squared plus 60 squared is, oh, it's the same thing, 3721. So that must mean that is a right triangle. And furthermore, these are a Pythagorean triple. They work. They work in the Pythagorean theorem. They work with an equal sign. All right, next one. Ooh, this one's got some roots in it. So what's the first thing you have to do? First thing is figure out the largest side c. All right, so first thing I'm going to do is plug in my calculator. 2 root 3, 4 root 2, and 3 root 5. Okay, so 3 root 5 is the largest of those three numbers. Okay, now I'm going to then see how that compares with that plus that. I'm going to compare them together. All right, so if you remember how we did this before, you apply the square to both. When I apply the square to 3, 3 squared is 9. When I apply the square to root 5, that just makes that 5. So this ends up being 45 on this side. Okay, over here, apply the square, it makes that 12. And again, apply the square, and apply the square. Oh, I almost did something silly. Root 2 squared is 2. That makes that 32. So how does 45 compare with 44? 45 is bigger, which means obtuse. There is one stipulation to this little process, and that is the not possible case. All right, not all three sides. If you just give me 3 random numbers, they're not always going to make a triangle. So this is the not possible case. If you remember back, here's what's happening. You have a length of 13, this long length of 13. You got this little length of 2 reaching out. You got this little length of 7 reaching out as far as that can, and they're just not going to reach. They're not going to make it. So before you even do these, you need to check to see if that's going to be the case. How do you check that? Well, you take the 2 smallest. Remember, the 2 smallest sides has to be bigger than the largest side. So it didn't. So that's not possible. All right, so with this lesson, when you get a right triangle, now when you get a right triangle, your first thought is Pythagorean theorem. I'm going to solve for a side or a hypotenuse using the Pythagorean theorem. Your second thought is, can I avoid it? Can I avoid the Pythagorean theorem by a 3, 4, 5 or 5, 12, 13? We'll see. And then this is the third type of question, is what type of triangle do the three sides make? Obtuse, right, acute, whatever.